Good morning, everyone. This is an audio recording for visually impaired student. Today I am going to read a chapter from Pradeep Organic Chemistry, Chapter 3 Organosulphur Compounds. Introduction. Sulfur is placed in the third period of the periodic table, just below oxygen in group 16. During the recent past, a lot of work has been carried out in the area of organosulfur compound, primarily due to their importance in industry and metabolic power process. Therefore, in this unit, we shall discuss some important aspects of the chemistry of organosulfur compounds. Structural feature. Both oxygen and sulfur alter the chemical nature of carbon atom to which they are attached, but unlike oxygen analogy, in most of the sulfur compounds, the reaction occur by the attack of nucleophile, an electrophile, or even a free radical at the sulfur atom. Another marked difference between oxygen and sulfur compound is that, unlike oxygen, which readily form double bond, sulfur is reluctant to form double bond by pi-pi overlapping. Thus, with the exception of carbon disulfide, thio compounds R2C double bond S are quite unstable and readily undergo addition reaction. In other words, thioaldehydes and most of the thioketones can be generated only as transit intermediate that rapidly undergo dimerization, trimerization, and polymerization to form compound having only sigma bond. For example, a thiocarbonyl dimer and a thiocarbonyl trimer. The instability of thiocarbonyl compound is primarily due to the difference in the size of 2p orbital of carbon and 3p orbital of sulfur, which makes 2pi 3pi overlapping relatively ineffective. In addition to poor 2pi 3pi overlapping, sulfur is also reduced to form 3pi 3p pi bonds with other sulfur atom. It is because of the reason that elemental sulfur does not exist as diatomic S2 unlike oxygen molecule. Instead, it preferred to form only S sigma bond and exist as a nonpolar octatomic molecule, acid having crown shape as shown in figure 3.1. Further, due to the larger size of sulfur atom, S bond is quite long. As a result, the two 3p orbital, one on each S atom, cannot come closer enough to undergo 3p overlap to a significant extent, and hence the pi bond between 3p orbital is very weak. It may, however, be noted that unlike thioaldehydes and thioketones, thioamides and thioacids are isolable and hence are relatively stable. This contradicts the generalization that pi bonds involving sulfur atoms are very weak. The actual reason for their stability is the resonance stabilization involving lone pair of electron on nitrogen or oxygen atom. Here, the contribution of structure second toward resonance hybrid of thioamide and that of structure 4 toward resonance hybrid of thioacid is significant because both of them have only single bond between C and S atom. We have discussed above that sulfur have little tendency to form pi bonds through pi pp overlap. However, many sulfur compounds such as dimethyl sulfoxide DMSO, a widely used aperiodic solvent, have pi bond between sulfur and oxygen atom. As anticipated, this double bond, like any other double bond, consists of an sigma bond and a pi bond. This sigma bond is formed by head-on overlap between the sp3 orbital of sulfur and one of the half-filled p orbital of oxygen. The other two sp3 orbital of sulfur overlap with sp3 orbital of two alkyl group to form two additional sigma bond, while the fourth sp3 orbital containing a pair of electron sulfur is now left with a half-filled d orbital say dxy or dzx. An oxygen also have a half-filled p orbital, say 2py or 2pz. Since dxy lie in the plane of 2py orbital and dzx lie in the plane of 2pz orbital, therefore d pi p pi overlap occur either between dxy and 2py orbital to form a pi bond. In the valence bond term, these d pi p pi bond imply that DMSO may be regarded as a resonance hybrid of the following contributed structure. Since DMSO has a high dipole moment 3.9 d, this suggested that structure first make a significant contribution toward the resonance hybrid, which of course is much greater than those of the structure third. An important difference between ordinary double bond with p pi overlap and sulfur oxygen double bond with p pi d pi overlap is that group attached to sulfur do not lie in a plane. This explains why acetone is planar while DMSO is non-planar. Structure of thiols and thioethers. Both in thiol and thioether, S is sp3 hybridized in a ground state. Such a sp3 hybridized sulfur has two half-filled orbitals which overlap with sp3 orbital of an alkyl group and a s orbital of a H atom as in thiols, or with sp3 orbital of two alkyl groups as in thioethers. Each of remaining two sp3 orbital contain a pair of electrons. However, due to greater lone pair repulsion than bond pair repulsion, the CSH bond angle decreases from 109 degree 28 minute to 100 in CH3SH. In contrast, in thioether, due to the greater steric hindrance between two alkyl group than between an alkyl group and a hydrogen atom in thiols, the bond angle in thioether is larger than in thiols. For example, methyl thioether has a bond angle of 105 degree. Structure of sulfonic acid. In sulfonic acid, sulfur is also sp3 hybridized. Since here we need to form two sulfur oxygen double bond, therefore both the 3s and 3p orbital are promoted to d orbital as shown below. The 4sp3 orbital of sulfur form 4 sigma bond, one with the carbon atom of the alkyl or the aryl group and 3 with the oxygen atom. Sulfur is now left with the two unhybridized d orbital which overlap with p orbital of two oxygen atom to form 2 d pi p pi s double bond O bond. The p orbital of the third oxygen atom overlap with s orbital of hydrogen to form an OH bond. Thus, sulfonic acid have tetrahedral structure. Nomenclature. For the purpose of nomenclature, sulfur compounds are classified according to the valence state of sulfur. The compound containing bivalent sulfur are structure analogous to the corresponding oxygen compound such as alcohol, carbonyl compounds, carboxylic acid, etc. Therefore, they are often named by adding the prefix thio to the name of the corresponding oxygen analogy. For example, thioalcohol, thiophenol. For naming the corresponding having sulfur in the place of carbon, the prefix thia is sometimes used, like thiocyclohexane. For compound having sulfur in the higher oxidation state, special names are used, like benzene sulfonic acid, dimethyl sulfone. Thiols or thioalcohols. Just as alcohol are alkyl derivative of water, in the same way, thioalcohols are alkyl derivative of H2S. Thus, the general formula of thioalcohol is RSH. In the IUPAC system, thioalcohol are called thiols. They are also called mercaptanes. Mercurium is equal to mercury, captanes is equal to catching. Since they react with mercury second ion to form insoluble mercury compound, Rs twice Hg, the functional group of thioalcohols is RSH. It is called sulfhydryl thiol or mercapto. A number of sulfur compounds are found in nature. For example, butane thiol is found in skunk, an American animal. Propane thiol occur in onion. Allyl mercaptane and allyl disulfide occur in garlic. Nomenclature of thiols. These are named according to the following system. First, common name. In common system, thioalcohols are called mercaptanes. The individual name of any thioalcohol is a derivative by adding the word mercaptane to the name of an alkyl group. Second, IUPAC system. In the IUPAC system, thioalcohols are called thiols. The individual name of any thioalcohol is obtained by adding the suffix thiol to the name of the hydrocarbon containing the same number of carbon atom. In case of isomeric thiol, the position of SH group is indicated by the lowest possible Arabic numeral. The common and IUPAC name of the some typical thiols is given below. In case of polyfunctional compound, thiol is named as a mercapto derivative of the principal functional group. It may be noted that OH group is assigned higher priority both in numbering and naming. For example, beta hydroxyethyl mercaptane, IUPAC name is 2-mercaptoethanol. Method of formation. Thioalcohol are generally prepared by the following method. First, from alkyl halide. When alkyl halide are heated with the excess of sodium or potassium hydrosulfide, thiols are formed. Second, from sodium alkyl sulfate or para-toluene sulfonic ester. When sodium alkyl sulfate is heated with sodium hydrogen sulfide, thiol is formed. Third, from alcohol. Mercaptanes are prepared from alcohol either by treating with phosphorus pentasulfide or by passing a mixture of hydrogen sulfide and alcohol vapor over thoria catalyst at 673 Kelvin. For example, ethanol in the presence of P2S5, it will give ethane thiol. Fourth, from alkene. Addition of hydrogen sulfide to the carbon-carbon double bond of an alkene in presence of nickel sulfide as catalyst lead to the formation of thiol. Alkene plus HSH in the presence of NiS 573 Kelvin, it will give 2-alkane thiol. The addition occur according with Marconic rule. Terminal thiols can however be prepared by free radical addition of H2S to an alkene. Alkene plus HSH according to anti-Marconic rule it will give 1-alkane thiol. Fifth, from thiourea or S-alkyl isothioureum salt. When alkyl bromide or iodide are treated with thiourea, S-alkyl isothioureum salt are produced. These upon alkyning hydrolysis give thiol in about 80 to 90% yield. This is the best method of preparing thiol. 6, from Grignard reagent. The reaction of Grignard reagent with sulfur powder give addition product which upon hydrolysis give thiol. Grignard reagent plus sulfur give addition product. On hydrolysis it will give alkane thiol. Physical property. First is a physical state and smell. Methane thiol is a gas while other thiols are colorless volatile liquid with disagreeable smell. The lower member have extremely strong smell while higher member have mild odor. The odor of freshly cut onion is due to propane 1 thiol and that of the garlic is partly due to propane 2 1 thiol. Small quantity of ethane thiol are added to LPG to warn against leakage of the gas. Second boiling point. Due to absence of hydrogen bonding, the boiling point of lower thiols have lower than those of the corresponding alcohol. However, thiols having 8 or more carbon atom have slightly higher boiling point than corresponding alcohol due to stronger van der Waals forces of attraction and weaker H bond. Third is solubility. Thiols are less soluble in water than the corresponding alcohol. This is due to reason that thiols cannot form H bonds with water. Fourth dipole moment. Due to small electronegativity of sulfur than oxygen, SH bond is less polar than OH bond. As a result, thioalcohols have lower dipole moments than their corresponding alcohol. Chemical reactions. Thiols resemble alcohol in many ways. The main difference in their behavior is toward oxidizing agent. Some important chemical methods of diols are discussed below. First, acidic nature. Thioalcohols are stronger acid than alcohol. This is because of following two reasons. First, bond dissociation energy of SH bond is much lower than that of OH bond. As a result, SH bond is cleaved more easily than the OH bond. Second, the anion left after the removal of proton from RSH. For example, Rs negative has a negative charge on sulfur atom, while in case of alcohol, Ro negative it is on oxygen atom. Because of the larger size of sulfur, Rs negative can accommodate the negative charge more easily than the smaller oxygen atom in Ro negative ion. Some important reaction of thiol due to their acidic nature are discussed below. A reaction with alkalis. Due to their stronger acidic nature, they dissolve in NaOH and KOH, forming their corresponding salts called mercaptides. The reaction is reversible and mercaptates are completely hydrolyzed by water in present in absence of alkali. Third, second reaction with mercury oxide. Being acidic, thiol react with mercury oxide to form mercury mercaptide. Third, action of alkali metal. Alkali metal being strong base react with mercaptanes to form corresponding mercaptide with evolution of H2 gas. Fourth, action of heavy metal salt. When a thiol is treated with the aqueous solution of the salt of heavy metal, for example lead acetate, a mercaptide is obtained. 2RSH plus PbOO CCH3 twice, it will give lead mercaptate plus 2CH3COOH. These heavy metal mercaptide are generally covalent compounds. Second, reaction of carboxylic acid. Thiols react with carboxylic acid preferably in the presence of all inorganic acid as catalyst to form the corresponding thioesters. The equilibrium lie mainly to the left. However, a good yield of an ester is obtained if acid chloride is used instead of an acid. Third, oxidation. Due to weaker SH bond, thiols can be easily oxidized. The nature of the product, however, depend upon the nature of the oxidizing agent used. With mild oxidizing agents such as air, H2O2, CuCl2, or sodium hypochlorite, thiols are oxidized to dialkyl sulfides. RSH plus H2O2, it will give dialkyl disulfide. An alkaline solution of sodium plumate containing sulfur also converted thiols to dialkyl disulfides. 2RSH plus Na2 PbO2 plus sulfur, it will give RSSR. Dialkyl disulfides can also be prepared by action of iodine on sodium mercaptide. Rs negative Na positive plus iodine, it will give RSSR. With strong oxidizing agents such as HNO3, protic acid, thiols are converted into sulfonic acid. This gives us an important point of difference between thiols and alcohols in their behavior toward oxidation. Whereas in alcohol, oxidation increases with oxidation state of carbon, while in case of thiols, the oxidation state of sulfur increases. Fourth, reduction. On treatment with nickel, thiols readily undergo desulfurization to form corresponding hydrocarbon. RSH in the presence of nickel, it will give RH plus NiS. Fifth, action of aldehyde and ketone. Thiols readily combine with aldehyde and ketone in presence of hydrochloric acid to form mercaptols and mercaptol. respectively. For example, acetaldehyde plus ethane thiol, it will give thioacetal, and acetone with 2 SHCH2CH3 called ethane thiol. In the presence of HCl, it will give dimethyl mercaptol. When these mercaptales and mercaptols in ethanol are refluxed in the presence of ranitidine, the thiol group is replaced by hydrogen. Thus, mercaptol and mercaptal formation in acidic medium followed by disulfurization with ranitidine give us an excellent method for conversion of a carbonyl group to methylene group under neutral condition. This method is however competitive with Clemmensen reduction, which is carried out under acidic conditions, and Wolff-Kirschner reduction, which is carried out under basic conditions. Further, these mercaptales and mercaptols on treatment with mercury chloride in the presence of cadmium carbonate regenerate the original aldehyde and ketone. Therefore, like acetals and ketols, mercaptals and mercaptols can also be used for protection of aldehyde ketone group in the acidic medium. Oxidation of mercaptol. Mercaptol are easily oxidized to sulfonols. For example, oxidation of acetone mercaptol with KMNO4 gives sulfonol. Sulfonol is used as a hypertonic, for example, sleep-inducing drug. Homology of sulfonol, namely trional and tetraonal, are even more effective hypertonics. Thioethers. Thioethers may be regarded either as dialkyl derivative of H2S or alkyl derivative of thioalcohols. They may be regarded as derivative of ether in which oxygen has been replaced by sulfur. CH3CH2 SCH2CH3. Nomenclature. The common name of thioethers are obtaining by additing the word sulfide or thioether to the name of the alkyl group arranged in alphabetic order. In the IUPAC system, thioether are named as alkyl thioalkanes. The sulfur atom is taken with the smaller alkyl group, which form a part of the alkyl thio group, while the larger alkyl group form a part of alkene. The common and IUPAC name of some thioethers are given below, like dimethyl thioether, 2-methyl thiocyclohexane. Method of formation. First, by heating potassium sulfide with an alkyl halide, potassium alkyl sulfate or potassium triosalate. Alkyl triosalate, it will give thioether in the presence of K2S. The yield are generally good to fairly good. Second, by heating an ether with potassium pentasulfide, ether in the presence of P2S5, it will give thioether. The yield are often poor. Third, by heating an alkyl halide with sodium mercaptide, CH3CH2 S negative Na positive plus CH3I SN2 reaction, it will give CH3CH2 SCH3 plus NaI. This method is similar to Clemmensen synthesis and can be used for the synthesis of both symmetrical and unsymmetrical thioether. Since alkyl sulfide is better nucleophile than alkoxide ion, the reaction is very rapid and give excellent yield. Fourth, by addition of an thiol to an alkene in the presence of peroxide. Cyclohexane thiol plus alkene, in the presence of peroxide, it will give cyclohexyl and propyl thioether. Fifth, by passing a thiol over a mixture of heated alumina and zinc sulfide at 573 Kelvin, RSH in the presence of ZnS plus Al2O3 at 573 Kelvin, it will give thioether. Physical property. Physical state. Thioether are colorless, oily liquid having unpleasant smell. Solubility. They are insoluble in water but soluble in organic solvents such as alcohol, ethers, etc. Boiling point. In general, Their boiling point are relatively higher than those of the corresponding ether. This is due to the strong van der Waals forces of attraction in thioethers as compared to ether, primarily due to the bigger size of sulfur than oxygen atom. Chemical reactions. Although ethers are relatively unreactive, thioethers are quite reactive. The reactivity is primarily due to the ability of a divalent sulfur atom to get converted into compound with plus 4 and plus 6 oxidation state. The main difference lies in the formation of sulfoxides and sulfones on oxidation and to form sulfonium salt with alkyl halide. Some of their important chemical reactions are discussed below. First, weak basic character. Due to the presence of lone pair of electron on the s atom, thioethers like ether behave as weak bases. As such, they dissolve in 100% H2SO4 to form sulfonium salt. R2S plus H2SO4, it will give R2S positive H, HSO4 negative. Second, reaction with alkyl halide. Being sufficiently nucleophilic, thioether react with alkyl halide by acento mechanism to form trialkyl sulfonium salt. A noteworthy feature of sulfonic salt is that they are tetrahedral, the orbital containing the lone pair of electron being considered as a fourth substituent if the three substituents attached to the sulfur atom are different. Sulfonium salt behave as chiral molecule and has been resolved into stable enantiomers. It may be noted here that tertiary amine of the type R1, R2, R3N could not be resolved in spite of fact that they have tetrahedral structure. The reason cited was that the energy difference between the two enantiomers was low and thus rapid interconversion between the two enantiomers gave a reciproc mixture. However, in case of sulfonium salt, the energy difference between the two enantiomers is sufficiently high and hence cannot be readily interconverted. Therefore, sulfonium salt can be easily resolved. These sulfonium salt are stable at room temperature but decompose on heating to alkyl sulfide. R3S positive X negative on heating it will give RSR plus Rx. With moist silver oxide, these sulfonium salt form sulfonium hydroxide which are stronger base. These sulfonium hydroxide decomposes on heating to form the original alkyl sulfide and a alkene. These reactions may occur either by E1 or E2 mechanism depending upon the nature of alkyl group. If all the group are primary, the reaction occur by E2 mechanism. If however one of the group is tertiary, the reaction occur by E1 mechanism. Third is formation of sulfur yield and their reactions. Sulfonium salt on treatment with the strong bases such as N-butyllithium eliminating an alpha hydrogen to form dialkyl sulfonium methylides commonly known as sulfur yield. These sulfur yields are extremely useful synthetic reagents and have been widely used for the synthesis of epoxide and cyclopropane derivating by reacting them with an ketone or an activated olefins as shown below. Fourth is oxidation. Thioether on oxidation first gives sulfoxide and then sulfones. With mild oxidizing agent like HiO4 at 273 Kelvin, oxidation can be stopped at the sulfoxide stage. Dimethyl sulfide in the presence of mild oxidizing agent it will give dimethyl sulfoxides. With moderate and strong oxidizing agent with moderate oxidizing agent such as H2O2 in glacial acetic acid, diethyl sulfide give first diethyl sulfoxide and then diethyl sulfone. However, with strong oxidizing agent such as KMNO4, HNO3, sulfones are directly obtained. Fifth, reduction. Alkyl sulfide on treatment with runny nickel readily undergo reduction and disulfurization forms forming alkane. 6. Reaction with bromine. Alkyl sulfide form many addition products. For example, addition of bromine give dialkyl sulfide dibromide. R2S plus bromine, it will give R2SBr2. Sulfonic acid. Sulfonic acid are organic compound having the general formula RSO3H, where R may be an alkyl or a aryl group. The aliphatic sulfonic acid are named either as alkyl sulfonic acid or as alkane sulfonic acids, while aromatic sulfonic acid are named as arene sulfonic acid. For example, para-toluene sulfonic acid, benzene sulfonic acid. Method of formation. Aliphatic sulfonic acid. Aliphatic sulfonic acid are generally prepared by the following method. First, oxidation of thiols. Thiols on oxidation with HNO3, KMNO4, NaOBr, etc. undergo oxidative coupling to form first dialkyl sulfide, which under the condition of the reaction are further oxidized to alkyl sulfonic acid via thiosulfonate ester or via sulfanic and sulfinic acid as shown below. Second, sulfonation of alkanes. Sulfonation of alkane with concentrated H2SO4, oleum or chlorosulfonic acid give alkane sulfonic acids. The sulfonic acid group generally enter the chain at second carbon atom. For example, N-hexane plus SO3. In the presence of H2SO4 at 330 Kelvin, it will give hexane 2 sulfonic acid. Third, action of sulfuryl chloride on alkane. The action of sulfuryl chloride or a mixture of chlorine and SO2 on an alkane in the presence of light or peroxide at 313 or 323 Kelvin give the corresponding alkane sulfonyl chloride in high yield. Here again the SO2 chlorine group enter mainly at the second position of the chain through a very amount of product with this group at the first carbon are also formed. Fourth, Stricker reaction. Sodium salt of sulfonic acid are obtained when an alkyl halide is heated with sodium sulfite. Rx plus Na2SO3 on heating it will give RSO3Na plus NaX. Fifth, addition of sodium bisulfite to alkene. In presence of oxygen or peroxide, antimarconic addition of sodium bisulfite to alkene give the sodium salt of the corresponding alkane sulfonic acid.